Hello there, Mr. Sutton here, bringing you this Pre-Cal Honors 6-1 lesson on polar coordinates and graphs. In this one, we will be plotting polar coordinates, converting between polar and rectangular coordinates, and as a real-life application, we'll be able to tell a robot which way to move. Let's begin by taking a look at the difference between rectangular and polar coordinates. The rectangular coordinates is the ones you've been using this whole time with x and y values. Looking at our x and y axis here, a point on one of these is just giving you the horizontal, that's the x, and the vertical, y, distance from an origin. Now the polar coordinates look a little bit different. Instead of an x and a y value, we have an r and a theta value. And those go with this sort of setup right here. Looks like a big target. Now instead of calling the middle of this the origin like we do over here, this middle is the pole, and this ray here, 0 degrees, that is the polar axis. And this point here, this r comma theta, that is giving us a distance from the origin or pole. That's the r value. It's just how many rings you have to move out at a specific angle, theta, from the polar axis. I think the best way to get an understanding of the polar coordinate system is to graph a few polar points. So for this first one, we've got 1, 150 degrees. The basic way of graphing these is to start in the center, start at the pole, turn whatever the angle is, and then take r steps out. So here we are in the pole. We're going to turn to 150 degrees here, and we'll take one step out to get to this point right here. Now how about 4, 420? Well, the nice thing about this is that just like the unit circle, you can add or subtract 360 degrees and still keep the same radius. You'll still be in the same place. So instead of writing 4, 420 degrees, we can write 420 minus 360, that'll be 60 degrees. So going back here, we turn to the 60 degree ray, and we take 1, 2, 3, 4 steps out. Now you don't have to do it in that order. You could take 4 steps out onto 0 and then go to 60. It really doesn't matter which order you do it in. Next one, 2, negative 30, we could express that as, well, pause the video and see if you can figure it out. All right, so we could express this as 2, 330 if we add 360. So here's 330, 2 steps out. And then this last one's a little bit tricky. Now we have a negative radius. Well, what does that mean? If we were just looking at 45 degrees, normally we would walk out in this direction. But this negative radius means we have to go backwards. So you'd have to go back 3 steps on the same kind of ray as 45 degrees. So that would be down to 225. If you don't like walking backwards, another way you can do this that accomplishes the same thing is to add or subtract 180 degrees, basically turn around, and then change the sign of r. So we could rewrite this as 3, 225, 45 plus 180 degrees. And then that would be going forward at 225 right here. Now that we know how to convert from rectangular to polar, what if we want to go the other direction and convert from a polar point to a rectangular point? So how could we find the rectangular coordinates for this polar point, 4, 65 degrees? And we want either exact value or nearest tenth for this. So what's going to help us here is if we remember a little bit of trigonometry with x, y's, and r's, recall that cosine of an angle is just x over r for the angle, and the sine is just y over r. So rearranging that to give us x and y, we know that x is then going to be the radius times the cosine of the angle. So in this case, that would be the radius of 4 times the cosine of 65. Sine is just going to be, or the y value is just going to be r times the sine of the angle. So that's going to be 4 times the sine of 65. And now we just have to plug that in the calculator if it's not already a special angle. So 4 times the cosine of 65 is about 1.7. And then we'll just repeat all that, except instead of cosine, we'll put sine. That's going to give us 3.6. So 1.7, 3.6, those are the rectangular coordinates for this polar point. At this point, we're going to see how to convert from a rectangular point to a polar point. So we're starting with an x and a y value, and we need to somehow turn this into a radius and an angle. How can we do that? Well, one way you could think about the radius, if you have a point on a graph, the radius is just going to be the distance from the pole or origin to whatever this point is. So if you pretend that these are the sides of a right triangle, you really are just trying to find the hypotenuse. That'll be the shortest distance from the pole to this point. So we can use r equals the square root of x squared plus y squared, basically the Pythagorean theorem. So we've got square root of -1 squared plus -4 squared, which is just going to be the square root of 1 plus 16, or the square root of 17. So there's our radius. Again, just Pythagorean theorem on the point that they gave you. Now, how about the angle? One way you could think about this is if you have a point, an x and a y value, you can use this to get the slope from the origin to this point. And if you have the slope of an angle, then you actually have the tangent of an angle. So if you use the inverse tangent function on whatever slope this gives you, you would get the angle itself. So that's what we'll do. We're just going to use inverse tan on the slope from this. So that's going to be tan of theta equals y over x, rise over run. So we can say that this angle is going to be the inverse tangent of -4 over -1. And we'll need the calculator for this one. So here we go. And yes, I did make sure I was in degrees first. This gives us a value of, say, 76.0. So that's our angle. Or is it? We have to be careful here because inverse tangent, you might remember, only gives you angles in quadrants 1 and quadrant 4. You can't get anything outside of negative and positive 90. So how do we know this is the right angle? Because, we're looking at the entire xy axis, and that covers more than just quadrants 1 and 4. So to figure this out, you have to compare the quadrant that your angle is in with the quadrant that the original rectangular point is in. What if they're different? If your angle and your point are in different quadrants, to get from one to the other, you just have to add 180, and that'll put your angle in the correct quadrant. So for example here, 76 degrees, that's quadrant 1. -1 comma -4, that is definitely quadrant 3. This is where the true polar point has to lie, in this quadrant here. So we have to change our angle so that it matches this quadrant. To get from quadrant 1 to quadrant 3, we just have to add 180. So that's going to be 76 plus 180 is 256 degrees. And by the way, this would work if you had a quadrant 2 angle that you wanted to, or a quadrant 4 angle rather, that you wanted to change to a quadrant 2 angle. It works both ways. So our final polar point then is going to be radius of radical 17, comma, 256 degrees. In a moment, we're going to give you a problem to try on your own. There's a backstory for this, though. Let's say we have an automated cleaning system that locates a mess at 3, -3 radical 3. It's an odd point. If a cleaning bot is in the center of the room, facing 0 degrees, there we go, how many degrees should it turn and how many feet should it move to clean up the mess? So if you're asking how many degrees it should turn and how many feet to move, you're basically asking for the polar coordinate of this thing that you have a rectangular coordinate for. So pause the video and see if you can put this rectangular coordinate in polar form. All right, let's see how you did. Let's get the radius first again. So we need, again, Pythagorean theorem for that. So r equals square root of x squared plus y squared. This time we've got 3 squared and 3 radical 3 quantity squared. Looks a little bit nasty. Let's do the easy one first. This is 9 over here. Now over here we have to square both of these things that are being multiplied. So this is 9 times 3, or 27. 9 plus 27 then is going to be 36, and the square root of all that is going to be 6. So that's our radius. That actually came out kind of nicely. How about the angle? For the angle, again, we have the inverse tan of y over x. So that's going to be inverse tangent of -3 root 3 over 3. And what does all that come out to? So plug in that craziness in my calculator. We get -60 degrees. So that actually did turn out to be a special angle. Now, -60, is that an acceptable answer? You are actually allowed to have positive angles in polar coordinates. Or negative angles too. However, we need to make sure that this angle, negative or positive, is in the correct quadrant. So let's see here. We've got quadrant 4 for negative 60 degrees, and the point that we're looking at, 3 comma negative 3 radical 3, down here, is also quadrant 4. Since the quadrant of the point and the angle match, we're allowed to keep the angle the way it is. We do not have to add 180. In fact, adding 180 would give us the wrong quadrant for the angle. So then our point will be 6 comma negative 60 degrees. And now we'll just tell our robot where to go. Right there. Go clean up that mess. All right. Another problem solved. For our wrap-up, we're not going to really do much. This is more of a show and tell, just to show you the awesomeness of these polar equations. Let's say we have the polar equation r equals 2 minus 2 sine of theta. How would we graph something like this? So we're not going to go through and do all the details, but the basic idea is you would take your major angles, special angles, plug them in to get r values to go with the theta values, and then plot all those points on the polar axis and connect the dots. This one, for example, would give you this neat looking shape, which is actually called a cardioid graph because, well, it looks like a heart. This next one, r squared equals sine of 5 times theta, has this neat sort of flower configuration. And if you don't want all the petals to be the same, this one's kind of a variation on the same theme. This one is kind of the simplest one of all, but the coolest in my book, r equals theta. That just gives you this neat little shape here, which is called the spiral of Archimedes. And then this one here gives you this nice little ball shape. And if you want to just kind of explode this and make a cat's cradle sort of thing, you can do this shape here. So these are all polar graphs, and there's just a lot you can do with this that looks very cool. So that's it for this first lesson on polar coordinates. Till next time, this is Mr. Sutton signing off.